Thank you. Okay, so I can see already that my slides are slightly misformatted, so some stuff's going to be cut off, but I think it's the same on the screen, so I'll try to point out what happens. All right, so the title of my talk in your brochure is Forest Products, and I'm going to talk about forest products in a very broad way, thinking about the different kinds of things that forest ecosystems can provide. And one of them is carbon storage in a natural state in wood, right? So one of the things that's been really a challenging controversy, and that I'm going to try to unpack a little bit today, is that the forest ecologists of the world have been pretty strongly supporting the idea that forests should be left alone, that that's a great carbon sequestration strategy of nature, and that the people who want to make bioenergy out of it have got it all wrong. And they've done a lot of analyses that suggest that it can take anywhere from decades to millennia to actually recover the carbon that's lost by inefficient use of that wood in a bioenergy situation. So many of you have seen studies of those sorts, and I spent some time a couple of years ago thinking this through a little bit, and I've been trying to figure out some simple ways to sort of organize the numbers and communicate the idea that there are actually some cases where there are really real challenges to making bioenergy make sense with forests, and some other situations where it makes a lot of sense, and trying to differentiate the two. So I'm going to talk about that controversy. I did want to just sort of make a little political note that in the US Congress this year, they've decided that carbon neutrality is not a scientific question, but a legislative question. And it strikes me that that's not particularly helpful. And I think that's important because, in my mind, photosynthesis is really a key to a carbon negative economy. And I'm pretty well convinced that we're going to need a carbon negative economy because we're overshooting 2 degrees, and we're going to have to take advantage of that. So a carbon zero economy, which solar and wind can do, that's okay, but I think bioenergy can do better, or biomass can do better, and it's bioenergy and biomaterials together, as you'll see. So there's 3 important drivers that I want to touch on. Ecosystem management. I really focus on conversion efficiency and co-products as some things that we need to be thinking about more as we do these carbon cycle analyses. And did want to point out that when we think about biomass, there are different kinds of feedstocks, and the waste and residues generally, their carbon dioxide emissions are already attributed to some kind of product, whether it's the corn grain that is associated with the corn stover, or construction demolition waste, or sewage sludge, or things like that. So there's no real carbon debt associated with those. When we think about energy crops on agricultural land, that there are some really nice synergies with other environmental benefits and ecosystems, and some soil carbon benefit. I'm not going to spend much time on that, but I will focus on the energy from forests and point out that when we look at the residues from forests, that those are mostly going to be going to carbon dioxide regardless of whether we capture that for energy or not. But there are some near-term trade-offs with carbon storage in trees, and we have to think about when those carbon benefits occur. If they occur 50 or 100 years from now, that's not going to get us to our 2050 goals. If they occur in 2020, that's a lot better. If they occur in 2016, even better. And this is just some data, a literature survey that Tom Buchholz and colleagues did a couple of years ago, a year and a half ago, looking at carbon payback periods from the literature, and you can see, again, sort of median or modal values of decades to century, and some outlier values that are really quite high. It turns out when you pack these numbers, a lot of this has to do with assumed efficiencies about the conversion process, and it also has to do with an assumption that all of the biomass is going to go to energy and none of it to materials. And so those are 2 things which are a little bit out of sync with reality in many cases, although probably not all. So one would think these are probably worst case scenarios. I did want to sort of recap for everyone's benefit, just some to point out that the forests have both above ground and below ground carbon, and that differentiation is pretty important. In our agricultural systems, most of the carbon stocks are going to be below ground in soil organic matter, and that's a real big difference. So a grassland is not going to store a lot of carbon above ground, so actually going out and harvesting a dedicated energy crop every year is a great way to use that carbon that would otherwise be decomposing in a year or two. But that is different in forests because of the wood's stability over time. And in temperate forests, it's about half and half above ground and below ground. Didn't want to really need to show this slide, except this is sort of, again, what the public views as kind of a worst case scenario. And if the corn ethanol world has to deal with food versus fuel, the forest bioenergy world has to deal with clear cutting as sort of a public outcry issue. I did want to provide a few accounting definitions. And these are, again, things that are used in the literature, but they're important conceptually. So business as usual, this is what would happen if we just kept doing what we were doing with a forest, which is harvesting it, some of it for materials and maybe a little bit for energy, but we're generally thinking about this as a forest that is managed as the U.S. Forest Service manages forests, as Weyerhaeuser manages their forests, as private landowners manage their forests, which are all quite different in different locations. Additionality is a credit for the increased growth that occurs when you harvest some of the wood in the forest. So when you take something out, you open up some of the younger saplings to lots more light. They will grow faster, and so there's actually an acceleration of carbon accumulation in the forest from management, and I'll show you some numbers on that. The carbon debt, which is essentially it's called a debt because in most of these analyses, the carbon conversion of the bioenergy is less efficient than some of the fossil alternatives. And I'm going to spend some time trying to compare those and show you when that occurs and when it doesn't have to be quite so bad. But when that does occur, then there's actually more CO2 emitted per unit of useful energy, so more CO2 equivalents per megajoule than some of the fossil fuels. And then the offset would be the fossil energies avoided by substitution. So I'm going to use a term then that I call carbon utilization efficiency. So it's the reciprocal of the CO2 emissions per megajoule, but for biomass over fossil. So you could actually flip those division signs around if you wanted to. But it's essentially I think this way of forming it shows you what an efficiency of biomass is relative to fossil energy or some other comparative value with respect to its CO2 emissions footprint. All right, so this is a paper, a fairly typical one, but had a nice, clear description from Mitchell et al. In 2012, looking at some of these terms. So here's the carbon debt. Theirs is spread over a few years because not all the use of the forest happens immediately. There's also the blue line at the top is the increased growth, so that's the accumulation advantage of managing the forest. And the initial debt is fairly quickly compensated for by the increased growth, so you get to this carbon debt repayment point, and then eventually, many years later, to a carbon offset parity point. All right, so this is sort of the short-term and the long-term equalization. And I'm going to be focusing on this carbon offset parity point in the analysis that I'll share.
Quick question, is discounting being considered in this?
No. And we've got a lot of economists in the room. We should be discounting, but it is not done. All right, so this is just to give you a sense of what the accelerated growth is associated with biomass harvest relative to business as usual. So in this case, we're taking out, let's say, from a unit of land that has 70 metric tons, we take off 20, drop it down to 50, and then the trees grow faster, and it takes maybe 100 years before it more or less catches up. All right, so that's sort of the concept. And depending on what your management strategy, those curves can look kind of different, right? So depending on the intensity of the harvest, et cetera, et cetera. So to simplify the discussion, I'm going to use an extreme example, which is going to be a clear-cut harvest. Okay, so probably worst case scenario in some respects, although in others it actually advantages the use of that material because it causes the most rapid growth to occur. And I'm going to use typical northeastern forest. Actually, the equation I'll use is a temperate forest. This is the distribution of the forest carbon in terms of the live tree, standing dead trees, understory, dead down wood, forest floor, and soil organic matter. And then because the harvesting event doesn't really change the soil organic matter too much, and this big number at the back makes it hard to fit a nice engineering equation to, I'm going to just look at the above ground material, which then the environmental engineers in the room will recognize as sort of a substrate limited Monod type equation, which is something that actually some foresters used. So this is the structure of that equation. Again, I'm an engineer. I don't want to spend a lot of time on this, so I won't even define it, but just to say that it fits that curve pretty nicely. And that there's a set of terms, actually, that I've found in the literature by McMahon and a group out of the Smithsonian Institution who actually provided all the parameters for temperate forests in the Northern Hemisphere. And this is their data. I'd love to talk to folks about this later. Actually, the reason that these individual forest lines are a little bit steeper than the curve is because of the increased carbon dioxide in the atmosphere accelerating forest growth over the last few decades, which is kind of a cool thing. But anyway, the general trend is quite stable, and so that curve fits. All right, now I want to spend just a couple minutes talking about the conversion efficiencies. And this is just literature data, mostly to show you that I've got, I got my T's crossed and I's dotted. A lot of that's from fairly critical studies of biomass energy. So Walker et al. Is the Manomet report. So many of you are maybe familiar with that if you've touched on forest bioenergy in North America. I also pulled some numbers out of the University of Freiburg. I think Chris has been there, so I spent some time there on sabbatical. Nachhaltigkeit, which is the word for sustainability in German, was actually invented by a forester in that area, and goes back, I think, 300 years. And what you'll see here is that these emissions of CO2 equivalents per megajoule are, well, they're relatively low numbers for the fuel production and transport. There's variation depending on whether you're doing thermal, electric, or combined heat and power in the combustion process for electricity and heat. And in general, the numbers for biomass are higher than some of the ones for fossil fuel, again, because of relatively inefficient combustion processes that are oftentimes used, whether it's a wood stove or a small electric power plant for biomass to electricity. And then I've used some biomass values both from GREET and also from some work that colleagues, Mark Laser in particular at Dartmouth, have done, looking at the overall emissions from biomass refineries plus the end of tailpipe emissions. Okay? So I've added that to the analysis for cellulosic ethanol, and that's a GREET number, and then some mature technologies that include ethanol fermentation, but also Fischer-Tropsch liquids and electricity, and in one case, electricity with carbon capture and storage, so geologic storage or utilization, and compared that to gasoline. Now, those are the raw numbers. When we flip those over in terms of that biomass utilization efficiency number that I was describing, here's what they look like. And so, in general, the biomass systems relative to these fossil alternatives, all right, give efficiencies in terms of their carbon emissions per megajoule of between 0.33 and 1.0. And the 1.0 is only achieved when you do carbon capture and storage with a very efficient, mature cellulosic technology. But combined heat and power, actually, if you're in an area which is burning oil, is also pretty darn good, and maybe not quite as impressive, but decent compared to natural gas. So anyway, there's a range of values. And then what I did is I put these into that forest growth curve and looked at this clear-cut strategy and analyzed how quickly we could reclaim that initial carbon debt. So here are the numbers, and remember that these are kind of the range is from 0.33 to 1.0. I'll start out with the green line, which is basically not doing anything. So we cut it, we don't use it, and it regrows, and it doesn't regrow all that much. Well, it regrows over 80 years, and then we cut it again, et cetera. And so that's sort of that situation. If we use it inefficiently, the 0.33 value, it takes roughly 80 years to get back to parity with the forest leaving it alone. So that's the kind of worst case scenario that we see in a lot of the forestry literature about these bad idea bioenergy projects. But if we get up into the 0.6 to the 1.0, we start to look a lot better. And the 1.0, of course, actually, if we're using it as efficiently as the fossil alternative, we get immediate turnaround payback. So there is no carbon debt. And the benefits relative to the natural forest are substantial over time, and they increase every time we harvest that forest. Now, you note I also put in a 1.5 value. That was not in the table I just showed you. But it turns out that that's possible if we use some of our biomass for materials. And that's actually something that's fairly extraordinary, and I think is an undertold story, is that many of these materials that we can use wood for have tremendous carbon emission reduction multipliers, in part because the wood is being used in a semi-permanent manner. So these are for timber frame structures, which are now being built into 10 and 12-story buildings, both in North America and in Europe. But also because the alternatives, concrete and steel, are incredibly carbon intensive, both because they both require a lot of energy to make the materials, but also because the chemistry of making cement from limestone emits CO2, and the chemistry of making steel from iron ore emits CO2, the coking process. And so you couple those things together, and there's some pretty big multipliers. So there's the carbon, and this is in the one case in this slide set where I've used CO2 emissions carbon, so I've reduced that by the 1240 force value that makes that ratio. And they're still up above 1, and sometimes up to 6, depending on the utilization. So using a conservative value of 2 kilograms per kilogram of carbon, and thinking about a relatively conservative value of 20% of the harvest going into these kinds of materials, then that increases the overall efficiency of that harvest by 0.4. And then going back to my earlier charts, even the relatively inefficient use of energy, the E equals, or epsilon equals 0.33 for electricity competing against natural gas, biomass electricity. If we used at least 20% of our materials, of our harvest as wood materials, and 80% for energy, we quickly get back to the point where it only takes a couple decades to turn things around. And if we use it more efficiently as either fuels or advanced fuels, or competing against combined heat and power or thermal purposes, we get these really big carbon benefits right away. So my talk. I'd love some feedback. I'm trying to figure out some good ways to communicate this to more general audiences. And so you're not a general audience, but so help me make it simpler and quicker, and I'll appreciate it very much. So did want to share